Hello friends, welcome to our channel Engineering Phantom. Today we are going to see the static noise margin analysis of 60 SRAM cell. So we have already done the static noise margin of 60 SRAM cell for hold operation. Now today we are going to do static noise margin analysis for read operation. So basically wasn't making video on 60 SRAM cell because I lost the access of Cadence tool. So I found a new version of Cadence tool, and I will make videos on how to do the analysis. I am not focusing on what values or result I am getting because it's a crack tool, so the values may be wrong, but you can get idea how to simulate on the license tool, so it will help you to do that. So to find the static noise margin, we have to do the DC analysis. So for DC analysis, we have DC source connected here at bit line. So let's select it Q, and we have given the value as a X volt. So basically just select all, delete, write X, press here, apply. Okay, so this way we can assign value X volt. So the SRAM cell schematic is done. I have made a separate video how to do the schematic. If you would have any issue in designing a schematic, you can watch that video. So the schematic is done, DC source is connected. Let's move towards simulation step. Launch ADEL. So this way the ADEL window will open. So here we have first of all assigned the DC values. So as we have connected the in-out ports, I prefer in-out ports because it will, to avoid confusion, the input output ports. Sometimes what happened, if we are connecting input ports, we have to assign it as the input value, and we can't connect the input port at the place of output values. Like we are giving the DC source, so we can't connect. If we mistakenly connect here output port, then in stimuli we can't find it to assign the value. So avoid that confusion, I am using the in-out ports for the conveniency, just for conveniency. There isn't written anywhere that you have to use in-out ports only. So as I mentioned, these are just ports, so we have to assign the values, and we will assign the values through here, stimuli or analog stimuli. Press here. So first of all, bit line bar, enable pulse, give DC value 1. So it will be first 1, then go 0, time period will be 20 nano. Yeah, let's move downward. So delay time, as we want instantly 1, so we will not mention anything. Rise type 10 pico. If you want to write, you can write, or you can leave it blank. Pulse width basically the time for which pulse will be on. So keep the period duty cycle 50%, we will use half time of the time period as a pulse width. So rest are some heavy parameters we don't need to focus. So press apply. Bit line is done. So I mean bit line bar is done. So bit line will be similar. Enable pulse 1 as DC value, 10 as a pulse, period 20 nano. Delay didn't mention, I will not mention anything. Rise time 10 pico, hold time 10 pico, pulse width 10 nano. This would bit line is done. Next is word line. Enable pulse UTC value 1. So word line will go from 0 to 1. Previously we have given 1 0 because bit lines will transit from 1 to 0. Word line will do transition from 0 to 1. That's why we done 0 to 1. So period is same, 20 nano. Next are delay time, as we want 1 after 0, so delay time will be 10 nano. After 10 nanosecond, the high voltage level will up. 10 pico, hold time 10 pico, pulse width, then nano. We are done with word lines. Next is ground. Ground is basically DC signal. Select DC, remove X, give 0, press apply. And I will like next is VDD, enable DC, press 1, value, apply. So VDD is done. So we are done with analog stable. I then edit variable. We have chosen X, so write same as small x or capital X what you mentioned in the voltage. So we mentioned small x, so here is small x. Expected value 600 nano. You can choose whatever. Apply. Okay. Next is add type of analysis. So we will assign variable same small x. Value will be varied from 0 to 1. Just apply. Done. Here as you can DC is there. The outputs we can take here or we can take here from schematic and take QB. Apply. This way we again return to ADLX simulation coverage at initial condition. So we are doing the read noise margin analysis for 0. We assign 0 to QB. Again write 1 to QB. Click on Q. So 1 is assigned. Give them as it is. So all the initial parameters are applied. We place on run and simulate. Let's see. And yeah, so there is no fatal error, so we will get the graph. Okay, so press on here x-axis, sorry, y-axis. Click on y versus y. Okay, so due to some reasons in my tool I am not able to do this. I can't drag this graph to here. So to bypass that error I will again do y versus y. Here I select another node. Okay, and in your tool you can directly drag your signal from here to here, so you have to do that directly, but I can't, so I increase one extra step and delete it, extra part. So this is the read noise margin of SRAM cell, our SRAM cell which I designed. So to improve it we have to, it's a very less, we can see the minimum square we have to fit here, right? Like I mentioned in the Hold noise margin analysis, or you can just directly do whatever values you got from the square, like just try to fit a square here, like vertical, press V, click here, press V, so you will get vertical line, yeah, like this. Press again V, hit H, H, try to find out where I, similar for here, and then length, here it's 6, what we can say 688, there, here we'll consider the values from here, yeah, 281, another one 261, so 261 minus 6, so we will get the noise margin length, then multiply it by cos 45 degree, we will get the read noise margin. This way we have done read noise margin, which is very less, so improve it, we can do the changes in the cell ratio, we can change the pull down and access transistors with to get the maximum read noise margin and improve. Okay, we can see the read noise. So I hope you understand. If you have any query or doubt, you can mention in comment section and I will try to answer them if I can. So thank you for your support, and I'll request everyone, please like and share our videos. Please do subscribe my channel, so it will motivate me more such